All right, welcome to the main topic of this module, which is Einstein's special theory of relativity. Now, our story really begins here. This is a sign of a younger Einstein in Bern, Switzerland, where he did some of his important work. And if you translate the German, it says that the special theory of relativity originated at Kramgasse 49, his street, in Bern, and the beginnings of the general theory of relativity also began in Bern. Now, general theory of relativity took him another 10 years after he finished his special theory of relativity. And before we launch into the details of this, if you happen to do some scientific tourism, you might look for the so-called Einstein house in Bern. And if you do so, all I can point out is it's easy to miss. I did it once some time ago in 2006, taking my family there, and it was just this sign on one of the entrances on a busy street that said, "Welcome to Einstein's apartment." So it's not quite the tourist attraction draw like Disney World, so just to point out if you happen to go there. But if you do, you can see this small, humble apartment, kind of historic now, right? Older style. The room's there, and you can read about his life and his works, and they have, for example, one of his original suits also that's seen in this photograph of him from back in the day. But okay, let's get into it. So let's start with Einstein's postulates, basically he formulated these postulates taking in what was known by then in the early 20th century. His first and main postulate is that the laws of physics, including electromagnetism, are the same in all inertial frames. An inertial frame, just to remind you, is a reference frame where the laws of physics hold. So by definition, any frame where the laws of physics hold is an inertial frame. But here we are saying explicitly electromagnetism must hold there. The second postulate is that every observer measures the same value c for the speed of light in vacuum in all inertial frames. So the speed of light in vacuum is 3 times 10 to the 8th meters per second, and basically his postulate is saying everyone has to get that measurement. Now really, this second postulate is a consequence of the first one, because remember, Maxwell's equations do predict electromagnetic waves, and it predicts that their speed of propagation is 3 times 10 to the 8th meters per second. So all we're really saying is that, yes, okay, we're believing in electromagnetism and it must hold in all reference frames. And that simple statement has enormous ramifications, as we shall see. These postulates embody Einstein's special theory of relativity, which was first published in 1905 in a paper entitled On the Electrodynamics of Moving Bodies. Later, he would incorporate gravity and acceleration into a general theory of relativity, and that took 10 more years for him to work on. Now, as in Newtonian relativity, there is no way to detect absolute motion. It's only the relative velocities between two inertial reference frames that matter. In some sense, this is democracy for observers. All observers are equal. And one way to phrase that is that if you have, say, a rocket move away from Earth, so we see it receding, an equally valid point of view if you are on the rocket is you see the Earth receding in the opposite direction. And those are two equivalent views of the same situation. Now, before we get into the consequences, let's go and define some basic things, some basic terms. First, events. Events are physical phenomena that occur independent of any reference frame. So, for example, a flash, an explosion, a snap, a return of a spaceship, or a disintegration of a subatomic particle. This is a physical event that happened independent of any coordinate system. Now, observers are let's say people who record events, both in time and spatial coordinates, in a particular reference frame. So you have an observer attached to a reference frame, and they can measure x, y, z in time for that particular physical phenomenon. For example, there might be a reference frame centered on Houston at Mission Control, which will mark down the time and location of a splashdown of a space capsule. In this case, the reference frame is that of the Earth, perhaps with the coordinate right, the origin right there in Houston, Texas. Now, simultaneous events, what is that? That occurs when two light signals from two events reach an observer at the same time. So two things happen coincidentally, and at least as interpreted by you as the observer. That's simultaneity. But there's a relativity of simultaneity. In other words, two events that are simultaneous in one inertial frame are not simultaneous in any other frame. And this is what we'll see is a consequence of Einstein's postulates. Continuing, let me introduce the concept of proper time, which is denoted T0, sometimes T naught, or with the Greek letter tau, which is like a cursive T. So we'll denote proper time, and that is the time difference between two events occurring at the same position. So say from the creation of a subatomic particle to its decay, it takes a certain length of time. We'll call that T naught. That is the proper time between two events happening at the same position. So if the particle is created at one point and decayed at the exact same point, the time interval between those events is the proper time. So in other words, you have to be in what's called the rest frame of that particle. So what is rest frame? Rest frame is the inertial frame where two events are only separated by time. So these kind of go together. It's the frame in which the proper time is measured. So if you're in a frame where an object is at rest and there are two events that happen, begin, end, the time between them, provided at the same location, is the proper time. Kind of likewise is the concept of proper length. This is the distance between two positions at rest. So my right hand and left hand, the distance between them, that's in my rest frame, that's the proper length. So it's the length measured in the rest frame, the frame where your object is at rest. Okay, if that makes sense. Okay, so if you're in the rest frame, you can measure time and length, and those are called proper time and proper length. And rest frame is where basically everything sits at the same position, and it's only time which is changing. Okay, so now let's get into the details of applying Einstein's postulates. In particular, let's talk about the concept of time dilation. So let's call that up. And here we'll follow kind of the classical example of illustrating this, which is with something called a light clock. A light clock is basically going to be two mirrors with light allowed to bounce between the two mirrors. Okay? So let's consider a light pulse bouncing between two mirrors in the reference frame of the mirror. So I'm going to call this reference frame S prime. And recall that the speed of light is c. At least I'm labeling it as c. So as the light bounces between the mirrors, by measuring the length, which we'll call L, and we can compute the total time for the round trip of the light pulse. So if we measure this length, VL, that's the proper length if you like, the time it takes for the light pulse to go up would be that length divided by the velocity, which is L over c. But to come back down is another L over c, so the total time for a round trip of the light pulse is 2L over c. So we can relate, therefore, the proper time for a round trip to the proper length there, L. So the proper time is 2L over c. Now, let's suppose we put that light clock onto a rocket, a spaceship, and it's going to travel at some speed v. And but we measure the round trip time of the light pulse in a different reference frame S down here, which is, say, the frame of the Earth. So the idea is we're putting this light clock on a rocket. We're going to send the rocket along at some velocity. The light clock's going with the rocket, but we're going to measure the time for it to go, the light pulse go up and down on Earth. So we're going to put our light clock on that rocket so we can see it move to kind of this trajectory with a kind of triangular directory, which if I illustrate that, here was the starting point for the mirrors when the light pulse left. Here's the ending point, and the light pulse actually traced out these two legs of a triangle. Now the transverse direction, that length will still be L. And now we can work out in the reference frame of the Earth how long it took light to bounce up and down as viewed by the Earth, okay? And we'll do this by just labeling the length of our legs. So that rocket that the light clock was on moved, let's say, at a speed v to the right. The total time that we're trying to calculate we'll call t. So I have a t in here in several places. How far the light clock moves in half that time is going to be the velocity of the spaceship times half the time, t over 2. So that's this leg. And then you add another t over 2 to get back to when the light pulse reaches the bottom again. So the total distance here is velocity times time, vt. Half that distance is vt over 2. Now, what about the light pulse traveling upward to the mirror? The mirror, of course, was moving to the right. So how long did it take the light pulse, say, to reach the top here, the distance L away vertically? Well, we know all observers measure the speed of light to be c, even when you're in the rest frame or even if you're in the Earth frame. So, okay, the light pulse goes at a speed c. How much time elapsed to go from the bottom to the top? Well, that was half the total time. That's t over 2. So c t over 2 is this distance, the hypotenuse of this right triangle here. This leg is length L, the horizontal leg is vt over 2, and then the hypotenuse is ct over 2. Does that make sense? I hope so. Okay. So now we can just rely on the Pythagorean theorem. We can say that the squares of these two legs equals the square of the hypotenuse. So L squared plus Vt over 2 quantity squared, which gives me V squared T squared over 4, has to equal Ct over 2 quantity squared. C squared T squared over 4. That's the hypotenuse squared. Or solving for L squared, just moving the V squared T squared over 4 to the right side of the equation, I have L squared equals C squared minus V squared T squared over 4. Okay, because two terms had a T squared in them. So I can use that to solve for t squared. So now it's multiply both sides by 4. Let's divide by the c squared minus v squared, and I get t squared as 4l squared over c squared minus v squared. And I can factor out maybe an extra c squared, so I have 4l squared over c squared, and that leaves me 1 over 1 minus v squared over c squared. So I just factored out this c squared from over here on the left side. So finally, if I take the square root, because that was t squared, because we were squaring a hypotenuse, remember. If I take square root of this line above is going to give me 2l over c. That's that common factor out front. And then I take the square root of this expression in parentheses, so the square root of 1 minus v squared over c squared. But wait a minute, let's look up above. In the rest frame of the light clock, the round trip time was 2l over c. And here's a 2l over c. So I can replace that with the time in the rest frame, that is the rest frame of the light clock, t prime. But the time we measure on Earth, as the light clock was moving by us with speed v, is t prime over square root 1 minus v squared over c squared. We didn't get the same time. And that's because the speed of light is always a constant. So yes, of course, if it is a longer distance light has to go, the longer the time it takes for it to do that round trip, right? So it makes sense. But it's telling us what we measure to be the time for the round trip is different. All right, so let's summarize this, because this equation here that I show at the bottom with the box is very important. So just summarizing here, we had two frames, the rest frame S prime and another frame S that was the rocket moves by, and we just measured in the Earth frame. So in the rest frame of the light clock, the total round trip time, as I said, was 2l over c. But in another frame, watching the clock move by with speed v, we put that light clock on this rocket and send it off to the right. That time, I'm going to write it compactly as t equals gamma t prime, where t prime was that rest frame time. Where gamma is now a shorthand, it's just a notation. It's going to be tiresome to write 1 over square root 1 minus v squared over c squared all the time. So it's traditional in special relativity to call this factor, 1 over square root 1 minus v squared over c squared, to be gamma. And t is just gamma times t prime. Much more succinct. Now, one thing to note is gamma is always greater than or equal to 1. Why is that? Well, v can be 0, so that would be 1 over square root of 1, which is 1, so gamma is 1. If v increases either negatively or positively, then I'm squaring it here, so it's a positive number, and I have 1 minus v squared over c squared. This can only be less than 1 in the denominator, even after you take the square root. So something less than 1 in the denominator means the overall expression is greater than 1. So gamma is always greater than or equal to 1. And what that implies is the time you measure on Earth when something moves by you is always going to be longer. And a word for lengthening something, stretching something, is dilation. It's stretched out, it's longer. But here's the curious thing. It also doesn't matter which frame is the clock and which one is the Earth. We talked about the rest frame being the clock frame and the Earth frame being a different frame where the clock was moving by. But we could have flipped the roles. You know, you could be on the rocket moving by looking at a light clock on the Earth. And so your light clock on the rocket, okay, the round trip time is 2L over c, but you look at the light clock on the Earth is receding away from you, and you say, wait a minute, it's running slow by the exact same factor gamma. It's a symmetric point of view. The clocks appear to run slow on Earth, according to the astronauts on the rocket. But you might think, well, wait a minute, how can both clocks be running slow? But this is an observer effect. This is often referred to as the twin paradox. If I have one twin on the Earth and one twin on the rocket, the one on Earth will see the twin on the rocket, their time stretched out. They will age more slowly, so the person should be younger when they return. But the astronaut on the rocket looks back at the twin on Earth and says, no, your clock's running slow. You're going to age less. You're the younger one. So who's going to win out? Who's going to be the younger astronaut when the astronaut comes back to Earth? So that's a little bit of a conundrum, but there's a little hidden thing in there because we're talking about constant velocities. And for the astronaut to come back, there has to be an acceleration. We'll come back to this twin paradox because it is kind of interesting, right? In a future lecture. And if I forget, though, don't forget to remind me. Okay, but do we have any evidence that this time dilation really takes place? In fact, we do. Let's talk about the experimental verification of time dilation. So, what is this picture showing us, which shows us a bunch of lines raining down on a mountainside? Well, what we're seeing here is an illustration of something called a cosmic ray. That is a particle from outer space, typically protons or other light nuclei. But as they hit the Earth, they will collide with molecules in the atmosphere, and they will create nuclear collisions, which create all kinds of unstable new particles. It's actually my field of research, particle physics. So we'll create these showers of subatomic particles. The longest-lived, most penetrating particle in that shower is a so-called muon, and we can see some here. They have a little Greek letter mu. Here's a muon. There's another muon. And it's an unstable particle. Its lifetime, average lifetime, is only 2.2 microseconds. That is 2 millionths of a second. Not very long, right? Now, they may have a lot of energy. Sorry, these were the pictures of the muons. I just circled them there for you. So you can find the muons. Those are actually the longest lived ones, even though it's only 2 millionths of a second. But if we didn't have time dilation, how far would these muons travel? Well, perhaps these are very energetic. There was a lot of energy, say, in this initial cosmic ray, create these particles, so the muons are traveling very, very fast. Let's say all the way up to the speed of light, c. So let's take the maximum velocity we think they could probably have, 3 times 10 to the 8th meters per second, but they live only 2.2 microseconds, which is 2.2 times 10 to the 6 seconds. Multiply these two numbers together, and I get basically 300 times 2.2, because the 10 to the 6 will cancel with 10 to the 6 here, give me only 660 meters. So we would predict, if all clocks run at the same rate, that the particle can only travel, on average, 660 meters. But the atmosphere is much thicker than that. It's kilometers thick. So how do we even measure muons on the surface of the Earth? Because it turns out you can put detectors, and we do observe muons on the surface of the Earth. The muons do travel kilometers. Well, it turns out with time dilation, I have to put in the time we observe on Earth for these subatomic particles, which means gamma times the proper time in the particle rest frame. So this 2.2 microseconds is t naught, the lifetime in the rest frame of the muon. Multiply that by gamma, and then the speed of light, and that's how far the particle can travel in our reference frame, the Earth's frame. And in fact, you could reach kilometers and thus be detectable at the surface of the Earth. And this is one of the pieces of evidence that shows that, in fact, there is time dilation. And to really verify this, because of course this is an average lifetime, there's a distribution, so you could say, well, maybe you're looking at the tail of a distribution, only the rare ones that live much longer. But you can study this flux of muons as a function of the altitude, like going up a mountain, which was done way back in the day. And you can see how that varies with elevation, and you can confirm effectively with some other complications because of the energy spectrum you don't know, but you can confirm this time dilation. So the fact that muons from cosmic rays reach the surface of the Earth is strong evidence for time dilation. Okay. Now there's a flip side to time dilation. So before ending this lecture, let's see this flip side. The flip side is what's called length contraction. So what have I done here? I've got two light clocks, but now I've oriented them horizontally instead of before I had them vertically. So two of them here. And we can use the light clock to define length based on the time it takes the light to make a round trip. Kind of the other way around, right? Before we define a time based on the length that it had to travel. So here's my light pulse bouncing back and forth. And we can define a length based on the round trip time. So we're going to call in the rest frame of the light clock that length L naught. The naught is kind of indicating that it's in the rest frame, just like T naught. Okay, in that rest frame, if it took T naught to be the total time to make one round trip, then the speed times T naught over 2, because it went one out and back, that was a round trip, so I have to divide by 2, is what I will define to be the rest frame length, L naught. So total round trip distance divided by 2 to get just the length. Now let's put this light clock on a spaceship traveling at a speed v, but measure the round trip time of the pulse to go between the two mirrors from another frame S, say that of the Earth, where the light clock moves by, just like before. The difference here is we've oriented the light clock to go with the light pulse going in the parallel direction to the motion of the rocket, or whatever it is moving this light clock. So we're having that light pulse bounce back and forth along the motion in the horizontal direction. So it started, say the light clock started here where these red lines are, and then a certain time later it's where the white lines are. So we can do some math to try to figure out how much distance or how much time it took the light to bounce between the two mirrors, and then calculate an effective length L. We want the length between the two mirrors as these mirrors move by us, as determined from the time it took for light to bounce back between the two mirrors. So it's a little trickier. Let me just define part of the time, T1, to be the time out, for the light to go from, say, the left red mirror to the right red mirror, as the mirrors are moving. And T2 will be the time back. So once it's at the red mirror, going back to the left mirror, as the whole rocket is moving to the right. So I break it into two parts, light pulse out to hit the one mirror, and then light pulse time back to go back to the first mirror. And the total time is just the sum of those two times. Well, we can argue it this way. When the light pulse leaves the left mirror, it's got to travel that distance L, right, to reach the right mirror. But in the time that the light pulse was traveling at a finite velocity, the rocket was moving to the right. So I have to add an extra amount of distance. The velocity of the rocket, or the light clock that is, times T1, that time that we defined to be to reach that far mirror. So the distance is more than L. It's L plus VT1. But whatever that total distance is, it has to be the speed of light times the time to get there, because the light pulse is moving at the speed of light to the right, eventually reaches the mirror, and that's CT1. So we can define and solve for T1, just move the VT1 to the right side of the equation. So it'll be C minus V times T1, then divide by C minus V, and we'll get the T1 is the length over C minus V. Right? Okay. Similarly, we can work out the time for the light to go back. So now when it's going back, the light pulse has to go to the left mirror. That distance is L, as measured on Earth, but that left mirror was moving toward the light pulse this time. So the distance is not going to be L that the light pulse travels. It's a little bit less. It's minus VT2, where T2 is the time for the light pulse to go back. And then what does that equal? That's the speed of light, which is fixed, always fixed at C, times T2, the time for it to go to the left from one mirror to the other. So we do the same gymnastics, bring the minus VT2 to the right side of the equation. That's going to give us a sum. C plus V times T2, divide everything by C plus V, and I get L over C plus V is T2. So now I have T1, I have T2, I can sum up and find T. So if I do that, here we go, sum it up, I write L over C minus V plus L over C plus V. I need to put them over a common denominator, so I'll do over C minus V times C plus V, which is going to be C squared minus V squared. So in the first case, I have to multiply by C plus V. By the second case, multiply by C minus V. Long story short, I get 2LC over C squared minus V squared for the total time. And I'm out of space, I'm going to have to move on to the next slide. So we left at 2L over C squared minus V squared to be the total time. But I can factor out a 2L over C. So here's 2L over C. And 1 power of C will have canceled one of the C's here. And so I have 2L over C times 1 over 1 minus V squared over C squared here. So basically I pulled out this C squared first. 1 power of it canceled with that C, so that gave me the 2L over C. But when I pulled out C squared from the denominator, I have to divide by C squared on the V squared term here. So that's why it's 1 minus V squared over C squared. Rearranging and solving for L. L is going to be C times T over 2. So I multiply both sides by C, divide by 2. I also have to multiply by the 1 minus V squared over C squared. And this is the total length, L, as measured on the Earth's frame as the light clock moved by us. Now, this is in terms of the time measured on Earth. Remember, the time measured on Earth is also different than the time measured on the rocket that's carrying the light clock. There's this time dilation formula, and here I expand out the gamma and say it's T prime over square root 1 minus V squared over C squared, which is the time, the dilated time on Earth for that light clock moving by. So now I can use this relation, plug that T in here to work out in terms of the light clock's proper time. So I'll do that, and what we'll get is when I plug this expression here in for T, I have 1 minus V squared over C squared to the 1 power here, divided by 1 minus V squared over C squared to the half power here, so I'm going to be left with 1 minus V squared over C squared to the half power, and then I have CT prime over 2. Or in other words, this CT prime over 2 was the proper length measured in the rest frame of the light clock. And then I have this extra factor, square root 1 minus V squared over C squared. So we can write that more compactly as L is L naught over gamma. Length measured on Earth is the rest frame length divided by gamma, where gamma is our shorthand for 1 over the square root 1 minus V squared over C squared. And so that is our basic expression for length contraction. Why do I say contraction? Well, because we know gamma is always greater than or equal to 1. This radical here in the denominator can only be 1 or less. So 1 over that is only 1 or more. So gamma is greater than 1, and I'm dividing the rest frame length by something greater than or equal to 1, which means L is less than or equal to L naught. Less than or equal to L naught. Length, therefore, is shrunk. It's contracted. There you go. But in some sense, length contraction and time dilation are really two sides of the same coin, where the coin is special relativity. Because in fact, we use time dilation here, in fact. So it's just two ways of looking at the problem. We either see the time getting stretched as something moves by you, that's always true, but also distances get shortened. The lengths get shortened along the direction of motion. So let me go back now to this cosmic ray muon and take an alternative viewpoint of what's happening here. Remember, we talked about these muons that have a short lifetime, and let's talk about what's happening from a different reference frame. Recall that these subatomic particles have a lifetime that's only 2.2 microseconds. But now, instead of being in the reference frame of the Earth, where the mountain is, let's take the reference frame of the muon, which is traveling downward. Well, in the muon rest frame, its time is just its proper time. So it only lives for 2.2 microseconds on average. How fast does it think it can go? Or sorry, how far does it think it can go? Well, 3 times 10 to the 8 meters per second. That's the maximum speed, say. Let's say it can't go faster than the speed of light. And it lives for 2.2 microseconds in its rest frame. So it says, well, I can only go 660 meters on average. Well, how do you get through the thickness of the atmosphere that's kilometers? Well, from the point of view of the muon, that distance between where you are in the upper atmosphere to the surface of the Earth, that length gets contracted shorter by exactly this formula we just derived. So the thickness of the atmosphere has shrunk by this factor gamma, just as the time was dilated in the reference frame of the Earth by that factor gamma. So from the muon's point of view, yeah, it only went 660 meters, but that's because the length of the atmosphere was shrunk by this relativistic factor. Okay, that ends this somewhat long lecture introducing you to Einstein's special theory of relativity.